Hello. Uh, I'm here to explain the third solution that I told you about. See, we have a map, okay, like this. We can actually utilize the Google Maps later. All right, so here it is. Let's assume that we have a map like that. All right, and the objective here is to find the minimum path between any two nodes. Every node is going to be defined by what I call CDR. So the C is the cost in dollars, the D is the duration in minutes, okay, and the R is an index that represents the risk. The higher the index is, the more risky the road is, okay? So each and every road segment, this is what I call road segment. I'm sorry, I'm going to be using my own terminology that I published before. Okay, so this is the segment. The segment is defined to be the link or the edge between two different locations, okay? So this segment is defined, every segment is defined by the cost in dollars, the duration in minutes, and the risk as an index. And if I want to go from this location to that location, I would like to find the minimum path, the path that would have a minimum combination of the cost, duration, and risk. So it could be this one, or it could also be that one, it could also be this one, and so on, okay? So what does it mean to have a combination of the three of them? It's a function, okay, that will translate the three inputs, the cost in dollars, the duration in minutes, and the risk as an integer, to a value, okay, and I call it the valuation process, or let's call it valuation, okay, which is an index or a value that represents a combined cost of the three of them, okay, for a single segment. So if you want to go from here to there, then the overall valuation would be this valuation added to this valuation, added to this valuation, added to this valuation, and so on, okay? So the valuation itself as a function, you can imagine it as beta 1 multiplied by the cost in dollars plus beta 2 multiplied by the duration in minutes plus beta 3 multiplied by the risk as an index. It will give you a single value that you can use it to measure. Pay attention that the sigma of the betas has to be 1, okay? So if this is, let's say, 0.6, so those together are 0.4. So this, if this is 0.25, this is going to be 0.15 as an example, okay? So this is how we get the valuation, and then the valuation of the whole pass is a function of the sigma of all of them, all right? The segments. So if you want to, again, go from here to there, then, and according to this path, it's going to be this valuation here, plus this valuation, plus this valuation to get you the overall valuation of the path, all right? How do we get the CDRs? The CDRs here are not fixed, okay? So they will be different from some time to another, which means that our environment, the map is our environment, is, we call it dynamic. And this is one of the benefits of the third proposed solution. It's dynamic, all right? So it could change actually, all right? And the dynamic behavior of this is being observed by IoT devices. Okay, and our IoT devices could actually be the vehicles themselves, right? So every vehicle is equipped with an internet ability that updates the cloud and so on, So now having this, you can actually see that, you know, the city or the country is now divided into regions. Each and every region could be a map like that, right? So each and every one is managed by a cloud, right? This cloud finds the model, which is the overall V for the whole graph, okay? And then if you want to go from a node here to a node there, then the two clouds will cooperate to find you the minimum path from this to that, okay? The solution here is, we call it federated learning. I'll talk about it for now, but before I talk about this, I want to tell you that, you know, the map is being modeled by a neural network, a very special neural network, a brain, okay, that looks like the map. But instead of having every circle to be a location, now every circle is a neuron, if you remember the lecture, okay, neuron. And this edge is a connection, okay, with the weight. This weight actually represents the C, D, and R. All right, that binds between this and that. Pay attention that this is a directed graph. So this could have C1, D1, R1 from V1 to V2. However, from V2 to V1 could have a totally different C2, D2, R2, okay? You tell me that doesn't make any sense. No, it does, actually. Imagine that you have two locations. The way from V1 to V2 is two lanes. However, the way from V2 to V1 is a single lane. So the duration, the cost, and the risk from going from here to there, V1 to V2, is going to be different from going from V2 to V1, all right? So this is what we call a GNN, this one, this brain, this neural network. We call it a GNN. The G is for graph and N neural and network. Okay, so this is a GNN. It's actually one of the neural networks that belong to what we call deep learning. Okay, so we're going to be using deep learning, a GNN, to model the map and extract the information of this graph to actually decide the path that we're going to be following when we move from location A to location B. All right. Let me stop here because I don't know if I can upload this to WhatsApp, and then I'll talk about the federated learning later.